There we go.
All right. Well, take it away. And thanks for being here.
Cool. Can you guys hear me?
Yeah, sounds good.
Okay, let me try to share my screen. I'm not used to this interface at all, so let's see how this goes. Cool. So can you guys see my screen? Awesome. Well, I did some presentation work, like just because it makes me feel more comfortable. Since this is the first time I'm presenting in Papers We Love, feel free to stop me at any point. Cool. So I'll start off with an introduction. I am a software engineer at Amazon in the Kindle log. I've been working about for 5 years now, all of it in Amazon. I did my master's from University of Texas in Dallas, and I did my bachelor's in India. I'm interested in reading and playing Go. I actually don't work in distributed systems, so my knowledge is very much from my master's. So it's about 5 years outdated now. So if I say anything that is not exactly correct, that's probably the reason. So cool. So the structure of this talk, basically, I wanted to talk about a shared log, mainly because I did not understand how it was an API for consensus as they claimed in the paper. I actually had to refresh on consensus itself. What is the well, the problem the paper is trying to solve, a bit about Delos, about what Facebook, what were they trying to do, what the VirtualLog abstraction, something about Loglets, and then how the reconfiguration protocol works. I'll be keeping switching back and forth between the presentation that I prepared, which is very minimal, and the official presentations that they gave in the Delos Usenix website. So without, well, I don't think, let's go for the next one. Yeah, so I'll start off with talking about a shared log. So the shared log is the backbone of Delos. The Delos is a storage system which Facebook built for their control plane. And the shared log is what they call an API for consensus. I did not understand, like basically you can see it written over here. I didn't understand the meaning of that specifically. So as I understand it, what it means is that once an entry is accepted into the log, you can assume all systems agree to it. So consensus can be done in different ways. And I guess by having a shared log, you sort of understand how the consensus took place. And that's kind of like what I understood as the shared log. Does anyone has anything else to add of what an API for consensus would mean?
No, that's what I got from the talk as well. Although I think that's a good summation. API for consensus. Yeah.
Sounds good. And then the other thing was which I wanted to sort of touch upon, which is not actually mentioned in this paper because it's sort of assumed as tribal knowledge, is what would be the target applications for a for a shared log implementation. And I sort of took it from the Corfu paper, which is something over Flash units. It's a Flash storage paper similar. It uses a shared log design. So the target applications that Corfu uses was a key value store, and I assume the shared log is used as a transaction log over there, a state machine replication library, and the other thing which I think recently, which I found out actually today, just a couple of hours back, is sort of Kafka is what would be effectively a shared log because it would effectively be a totally ordered broadcast channel. So that's kind of like what Kafka and Kinesis and all of the other applications that rely on sort of windowed event streams would be a good application too for this one. Cool. So that's my small sort of just bit of me trying to understand about what shared logs were. So now what the problem is, the paper is trying to solve. The paper is basically trying to, so the paper basically, they wanted to build a control plane storage system. They didn't. But what they wanted to solve at the very core is that there have been a lot of advances in consensus over the years. Raft is about, I think it's about 8 or 10 years now, or even more than that probably. Paxos is even older than that. It's about 2000, I think. And so basically there's been implementations like Corfu, which is about how would you do a shared log on a storage cluster. You've got like databases like Tango that have come out with all different designs, and they sort of wanted to build something that they didn't have to swap out. They didn't have to swap out every time they wanted to upgrade the consensus algorithm. To think about that, I sort of tried to think about what would it take to swap out a consensus algorithm, and one of the problems that exists in a consensus algorithm, which I saw, was that you can't actually replace the consensus algorithm without in midway. Like you would have to sort of create a equivalent Raft state for an equivalent Paxos state, and that's how you can do a hot swap if you wanted to do something like that. So a hot swap seems like a harder problem to solve. What we could do though is we could just stop the consensus at some point, and then we could open it up. We could sort of move it to a new protocol, and then restart that protocol up. But that would sort of cause service downtime, which in today's world is not an option. So that's kind of like the two things that's kind of like the main thing that the Delos engineers were trying to solve. And then they wanted to develop a new shared log, which basically they didn't want to re-implement multi-paxos, although like the ideas of this paper are heavily derived from multi-paxos. They sort of try to expand the idea of shared acceptors, where the reconfiguration from one set of acceptors to another set of acceptors to sort of expand it into a more general protocol-based approach. So that's kind of like the general idea of what they were trying to do. Yep. Then the next one is So I'll talk a bit about the Delos runtime and how they sort of wanted to how they sort of wanted to create a isolation layer that would allow independent updates. So what the Delos runtime they're trying to do is they've got the Delos database layer. So this would sort of have your Delos SQL, maybe like you could use SQL on the database. You could use NoSQL semantics. You could use like Zookeeper semantics. The API layer over the top could be anything you would like. At its core, they use the Delos runtime as they use the runtime to sort of they use the runtime to sort of act as a client into the virtual log, and the virtual log is effectively a transaction log, which they use for providing the Delos table. There are implementation details about how the Delos table is constructed and like what the virtual log is, which I'll touch upon in a bit. I've focused mostly on the higher level abstractions and some of the things on the specific loglets, but not on the specific implementations as such too much. So that's kind of like what the Delos storage system is. I'll take a pause over here before I get to the next one.
It's all pretty straightforward so far.
Yep. Yeah. I just wanted. I can't see the chat, so that's why I just wanted to make sure.
No. The only comment is that the Kafka topics are not totally ordered, but Kafka topic partitions are totally ordered. That's one of the comments. I was just posting some of the papers, so yeah, you're good.
Yeah. Awesome. Cool. So then let's start talking about virtual consensus, and this is kind of their solution to sort of change the protocol midway. So they wanted to. So Delos engineers wanted to effectively change the protocol midway, as I sort of mentioned before earlier that without really chopping the old protocol, there's no real good way to sort of hot swap the state over. So I think so they effectively what virtuous consensus boil down to is sort of providing an API and stopping the old protocol at its at its core. And we can walk through all the components. So at its core, there are three components. We've got the virtual log, the metastore, and the loglets. The virtual log is effectively a virtualization API. And so I'll start talking about that one first, and then we can go to the loglets, and then we can go to the metastore. So, and then the reconfiguration. So the virtual log implements a logical shared log by chaining underlying loglets. This sort of comes from the kind of obvious notion that if you break up a log into multiple logs, the individual logs are effectively, you can chain them together to form a new log, which is this which would be the same thing if you written all the entries into one log. So so they provide all the basic log APIs. You've got the append API, as a log is just an append only data structure. So for a regular log, it would go to the last entry. For the virtual log, it would go to the last loglet in the chain. So you can imagine a virtual log as, say, let me open up their presentation because they sort of have a good picture. So you can imagine, like, this is what the virtual log would look like. You can see there's a zookeeper loglet, and they have an LD loglet, and you can have multiple other loglets too. And effectively, this is what the virtual log, the metastore, and the loglet look like at a high level. The virtual log provides the APIs to the clients. Let me just go back to so the virtual log provides the API to the client, which is effectively the three APIs. Actually, there's a fourth one called trim2, but there's four APIs which it provides to the client. There's append, which for a regular log, it would be the last entry. Virtual log, last loglet. Checktail, same thing. It would be the index of the first one. So this is directed to the last loglet in the chain, but it is remapped into the metastore. So it is remapped into the virtual log address space. So, and then the read next is effectively gives you the first entry in the address space. For multiple loglets, as I understand it, it goes one by one to each one. It'll do the read next. If one of them, I think, like, it'll go from the bottom to the top for multiple loglets. So let me just walk through how the configuration is done for the virtual log. So and by configuration, I mean that how the loglet is kind of how do the virtual log map to the loglets. So effectively, what the virtual log defines is an infinite address space that that they map to the virtual loglet. So they don't have, so there is no requirements of the indices needing to be the same. So if we put, like, let's say this is 0, this would be 1, this would be 2, this would be 3. This could be like 123, for example, or something of the sort. This could be 123, 124, and so on. So and this mapping is stored in the metastore. So the virtual log, they provide, for the client's perspective, there's a log which has a consistent virtual address space, and they don't have to understand anything about what the loglet's individual address spaces are. So yep, that should. So then it sort of provides reconfiguration API. This is basically, so we'll be talking about the reconfiguration protocol, but I didn't actually write down the APIs because I found that a bit counterintuitive. Counterintuitive in the sense, like, I found it better to understand the reconfiguration protocol first and then come back to the reconfiguration APIs. But there are three of them. We'll keep that in mind, and I'll come back to it after I talk about the reconfiguration protocol. So far, we've spoken about the virtual log. We've spoken about how the address space that it holds, and it tries to map it to the loglets. So let's move to the loglets itself, which is what they have to do. So, which is each of the segments of the log. At the most trivial level, it would be it would be a one loglet with an infinite log. So that's kind of like what would be the most trivial level. And then effectively you cut off segments and you can create multiple logs. They have to implement total ordering with durable storage. But they don't have to be highly available. So they don't have to implement fault tolerant consensus. They just have to implement consensus. So I mean, so basically everyone has to agree on the order of the logs, but they don't have to be available all the time to be the loglets themselves don't have to be available. The only source of fault tolerance in this paper is the metastore and the virtual log themselves. So, and we'll get to that about how all of those things fit together. But basically, you've got your regular log APIs. There's a seal command, which basically you seal the log. So effectively, if you go back to this paper, this point you've sealed the log. This is effectively this the virtual log calling some of the client calling seal on the loglet. So I just wanted to like call out one thing in the paper which I totally didn't understand. But if you go to the sorry, I didn't position this already. But yeah, if you go to this, it extends the Loglet API. So effectively, the virtual log has a seal API. My guess is it goes to the oldest one. My guess is it automatically goes to the latest one in the log, like append and append read next. But they don't actually talk about it in the paper. Cool. So let's go to the checktail returns the seal status. So again, if it's true, it's true. If it's false, it's false. The seal has to be highly available. So effectively, a log that has been sealed cannot wake up and suddenly decide that it's not sealed anymore. So it has to be highly available in that sense. Even in the presence of fault tolerance, like it has to. If a seal succeeded, the log can never the loglet should never become unsealed effectively. Cool. So the other thing is that, so just sort of like notes of mine, a success field does not prevent future appends to be written. They just need to be marked as an error. So I don't really understand this very well, but it happens. It's important for the native loglet to repair and the striped loglet, which they have the two implementation. But what that means is that if you go over here, and so at this point we've effectively sealed the first loglet. And so now we have 0 to 3 mapping to the zookeeper loglet. But if I try to write to this one, it will give me an error, but it might actually write the value over here. So that is a possibility. It doesn't matter from the virtual log perspective because no clients would actually see the error, see the entry, because they are mapped on the they are only mapped to the mapping prevents them to see this entry. So even if you write more loglets, even if you write more entries, it does not matter as long as the metastore is updated and the seal position is there. So that's. I'll pause here for a second, just in case people want to talk about something.
I think the loglet piece is the real interesting innovation here. It's like the way you can seal logs is really interesting.
I think it's there fundamentally to solve an engineering problem, right? Which is doing upgrades and stuff. I don't think there's much. Personally, I don't find the protocol much innovative. It's just that by sealing, you're able to use multiple backends in the background and evolve the system.
Yeah, well, it's not just that you're able to use multiple. I think for me the big thing is that you're marking them error, as opposed to failing the entries. So it means that your system is like, if the log keeps getting writes because your log isn't like fully consistent, it doesn't matter as long as your metastore, like the seal on the loglets is, because if I write the same record to 2 loglets, it doesn't matter if one's sealed. And I think that is kind of innovative. Rather than going with error approach, you go to recovery approach.
Yeah, I mean, it is introduced because you have a extra level of indirection, so you need to manage that, right?
Yeah.
It reminds me a bunch of the tombstones and some of the CRDT algorithms, because they basically figured out you can't store infinite history. We got to figure out a way where you can actually put a pin in it and say, okay, we can go back up to that point. So yeah, the tombstoning thing reminds me a lot of that.
Yeah, I found the Loglets pretty cool. I mean, it's like a lot of distributed systems. At least this is my opinion. In hindsight, it seems pretty basic. And this is what when I understood time clocks, Lamport's first paper. Like in hindsight, that seems pretty like almost like not, I wouldn't say obvious, but basic, but but just thinking about like coming up with it seems like some amount of like you had to change your perspective a little bit. That's what I find fascinating.
Did they talk about what's the overhead of having this extra level of indirection in performance?
They did speak to it a little bit, but I didn't read too much on that. So it sounds like they didn't have too much overhead on it, and they talk about the performance of switching the loglet from the Zookeeper log to the native log. And for the most part, their implementation seems like they've used client-side libraries and an embedded metastore, which is in the Delos servers itself. So it didn't look like there was any additional overhead from their implementation perspective.
You should be able to get it pretty lightweight, except for the extra calls to the metastore for the redirects. Like you have actually extra network calls, your redirects, and then everything else is like garbage collection and post process, which shouldn't impede the. So unless your thing gets into a bad state, I guess if you get into a bad state, you might have some issues. But at a normal state, you just extra network calls, which are relatively low versus the cost of consensus, and metastore calls. But if you're using any sort of like cache-based metastore, I guess you want some amount of persistency, but backed up Redis or Memcache or something should get you decently fast.
And if it is larger than what will fit on one server, you're going to pay that cost anyway, because your first hit's going to be, hey, what servers actually got the blocks that represent my log? Now I'll go talk to that server.
That's fair.
Hopefully,
it's like the GFS master.
Doesn't the client library or the client, the top node basically cache all that information to figure out where to route the requests?
In the Delos implementation, they do. So okay. they have mentioned that you can cache the metastore, and as long as there's no reconfiguration that has happened, you're good to use your cache stuff.
Okay.
Yeah, that's a good point too. That loglets replace some of the. You're actually replacing some of the the finding the master routing of an algorithm with loglets to be just the core of the shared log, and you're taking on the responsibility of some of the routing yourself, which requires a re-implementation of some of these algorithms. That's theoretically fixed cost.
Cool. Sounds like anything else. I'll move on to the metastore. Metastore is effectively a single version register that supports a conditional write. So if and we'll sort of get into it in the protocol, but basically to write to the metastore, you have to give its version. So you basically say, if you are version 1, then write my entry effectively. So that's how this is built. in the paper they mentioned this, which is like this is the only necessary and sufficient source of fault tolerant consensus. So it doesn't mean that the loglets can't be fault tolerant, but they don't need to be. So you don't have to implement Raft or something like that. You can implement something that isn't fault tolerant, and the metastore kind of handles the fault tolerance because of the reconfiguration. So the metastore is implemented in because the reconfiguration doesn't happen that often, the metastore is in Delos is implemented via Paxos. Any algorithm would work, but they've just implemented it with the just the regular Paxos, which was in Lamport's original paper. So because they don't need it to be, it doesn't have to be fast because it's only written occasionally. Cool. So let's get into the configuration itself. There's three parts to the reconfiguration. You seal the current active chain. So this is an idempotent operation. Multiple clients can try to seal. Yeah, and to start off with, this is a client-initiated operation. So there is 3 times this can happen. Either the client initiates it, which is effectively you could consider an operator sitting on a CLI deciding a change. The second one is on the VirtualLog can decide to trim out some of its previous ones. So, for example, if you were trying to do a trim on the previous on the 1 to 3, and then suddenly this actually does not have any log entries anymore. So the VirtualLog itself decides to remove the top entry out of its own out of the metastore, so that because it does not have anything anymore over there. And then the third one is in terms if you don't have fault tolerance in the loglets, then the reconfiguration, then the loglets need to implement failure detection, where it can sort of tell the metastore to reconfigure when it detects a failure. That's kind of the 3 times that this is expected to happen as per the protocol. The protocol is pretty simple. Seal the active chain, install the new change to the metastore, and then you fetch the new chain. So and I was planning to walk through sort of what would happen, like if certain failure scenarios happen, the general example that they've given in the paper, what happens in certain failure scenarios, what would be the expectation as per the paper, and so on and so forth. So this was like my 2 slides to show the example on the official paper. So I'll go official presentation. So let's just walk through the example over here. So we have like a client that's on a VirtualLog. It has a zookeeper loglet for first time. We have a metastore which has 0 to infinity with zookeeper loglet. Then you seal the loglet, and then the second step is install the new configuration on the metastore. And so that's the second step. So effectively, after this point, the new loglet is active. So clients can start writing to it. The third step is in case if the third step is mentioned in case of multiple writes. If you were in the winning configuration effectively, then you have to fetch the new entry to try again. If you wanted to try again, that is an optional thing. So this is basically this is how you deploy the new loglet. So that's kind of like the general idea. So so I plan to walk through a couple of failure scenarios. So let's start off with what happens if multiple a couple of edge case scenarios, actually not failure scenarios, but let's start off with what happens if multiple clients try a seal. Well, the first one tries a seal, which sort of causes this. It sort of causes the client to get sealed. The second one tries a seal. Oh, I don't know what happened over there. Just give me a second. This became too big. Yeah. So the second one tries a seal, and effectively it's already sealed. So I think you can just send an acknowledge back that it has been sealed already. So that's kind of like how a multiple seal would work. Then we can go into the next step where loglets are trying to install on the metastore, right? And so we've got we've got a fault-tolerant consensus protocol running on them. So we can assume that that this we can assume that the first client is trying to write a entry of like it's going to write that the new entry should be 3 to infinity as a Paxos loglet, and then we can assume that the second one writes whatever it was going to write in the first place, which was basically, I think it was LD loglet. So it was like 3 to infinity LD loglet. Both of them have a conditional, so it's if version is equal to 3, if version is equal to 2, this is like the version 0. So if version is equal to 0, write my new version, both of them write. Because it's a fault-tolerant consensus protocol, only one of them would win. And the second time this one would sort of, so one of them would win, one of them would lose. So we can see that if the 3 to infinity LD loglet wins, we would get like version 2, which basically says LD loglet, which is what happens in the paper. But like, and then this would fail because it's a version write. So this is version 1 effect. This would be version 1, and the condition doesn't match anymore. So that's kind of that failure scenario. Yep, and I think those are the two main ones where effectively, right. And then what happens if the host crashes? Is the last one that I want to talk about. So we talked about race conditions. So what if like now this client initiated the seal, and it crashed before it could write into the log? So basically, this one's effectively dead. What will happen, as per the paper, is that this client, assuming, is going to try to write to the log. So it tries to basically say append, and which it, let me just label it. So it says append, and I think that's a bad color. It says append, and it'll get an error, which will get append error. So what it notices that and so what it'll do is try to fetch a new metastore configuration because it's because it thinks that, okay, fine, there is a metastore, there must be a new entry in the metastore. So what happens is it goes to the metastore, it comes back, and then it sees that there is no new entry in the metastore, so ZK loglet is still the right one to write. So it waits for a timeout, and once it waits for a timeout, it will write the new. It'll try to just continue the reconfiguration. So any client can complete the reconfiguration. Here's the call out that the paper gives is that this client has no clue what this client wanted to do. So this might be, this might be, it's trying to write a new entry of like the LD loglet, but that failed. So it has no clue. What the paper says it does is it just writes a new entry of like 3 to infinity is also a new instance of ZK loglet. And I assume it can just be any loglet as long as it just writes a new version to the register so that everyone else knows what the new loglet is. And that's kind of like what happens when the client fails after the first step. So I think that covers most of the reconfiguration protocol. I'll just pause here for questions and things.
It is always funny to me that this algorithm is like, this paper is like, yes, let's virtualize the shared log because that's a way of virtualizing consensus. And our metastore needs to implement Paxos.
Right.
Like, you need to our metastore must have some form of consensus algorithm implemented on it, or this thing should fall apart.
Isn't the metastore abstracted inside the system though? When users don't need to implement it.
Right? Yeah. It's just funny to me.
I mean, you need consensus in some shape or form, right? I mean, even the Zookeeper and other underlying loglets are implementing consensus of some sort.
Right, and that's one of the things we'll get to. It doesn't have, the loglets don't have to implement consensus.
I mean, what happens if you just write to one place and you lose the data?
Sorry, doesn't have to implement fault tolerant consensus. So it doesn't have to bring up Paxos or anything of that sort which is available. It does have to be consensus. So it does have to agree on the log order.
But how many copies of a log entry are stored in the system for fault tolerance?
Sorry, I didn't understand that.
How many copies of, so if a user writes something, how many copies of the data are stored?
In the protocol they gave, like, so I can talk about the next part a little bit, which is basically the, so you can see over here that you don't have to be fault tolerant consensus, you only need to be fault tolerant seal. But basically what they have is like, they have a single sequencer algorithm which does not do reconfiguration on the leader election. So if this goes down, sorry, if this goes down, it's down.
Okay.
Yeah. Right. So that's what it means by not fault tolerant consensus. So it does have consensus and it does do replication for fault tolerance in terms of like a data loss, but it doesn't do fault tolerance. Like it can't keep going if this one goes down.
So it has a single point of failure on the sequencer, basically.
Right.
So this, I'm sorry, I may have missed. So the sequencer is different from the metastore?
Right. This is a new loglet that they've defined.
Can you do me a favor, and when you're not speaking, can you mute? I think you might be the feedback. Okay. Continue, sorry.
Yep, so, yeah, so basically, yeah, so the native loglet is, I can just sort of like talk about the native loglet really quickly so that we can sort of use that as a basis of the discussion. So the native loglet is a new loglet protocol. It's not a, it's basically what you would put underneath the metastore. So effectively, instead of the LD loglet, you could assume that this is a native loglet. So, you know, like you've got the native loglet over here. So it's actually underneath the protocol. And so you could, yeah, so, and this goes, like, this will be like, it'll be 3 to infinity for that. And so, and all of these things, the new ones would be the native loglet. Going to the sort of, so let's just walk to the consensus algorithm, which is the native loglet implementation. All the writes go to the sequencer. So everyone, right, all the clients write to the sequencer. One of them is designated as a sequencer. So effectively, like each component over here has a client, a log server, and one of them are this. So these are all embedded components. So you'd have the sequencer and you'd have these three. So effectively, when this goes down, you can't. This protocol basically does not know how to do reconfiguration. So it does not need to. It does not do the reconfiguration itself. What happens is, let's say this detects that it's failed, right? So this one tries to write something over here, and it detects it's failed. What it does is it basically tells the virtual log that. So it effectively will tell the. It will effectively initiate a reconfiguration. So it will initiate a reconfiguration itself. And what happens is it can do, and there are multiple ways to do the reconfiguration, but you can imagine that if you have a second loglet, which effectively this is a sequencer now, you could just put it back to the same loglet, but same instance of servers, but with a different sequencer implementation. And so now on the metastore, like if it would be, like it would be 0 to infinity is the first loglet. The second loglet would be like the second version would be 3. It will change to 0 to 3 is native loglet 1. I'll change the color a little bit, and it would be basically 3 to infinity is native loglet 2. And so effectively this, the loglet itself does not have to implement any consensus. It doesn't have to implement fault tolerance in the consensus effectively. The way this works in terms of the metastore is that you can seal, and I can just walk through how this works. So in case like so you can run to all the log servers for a check date. You can on the local reads are in the log server, and then we can go to the here they describe if the sequencer crashes. What happens is the one that detected the failure will seal both of them and initiate a reconfiguration. And so it's a fault tolerant seal on the loglet, and that's what happens. This is their switching logs mid-flight. They found basically a significant drop in latency when they switched from the Zookeeper loglet to the native loglet. So that's kind of like what they mean by the loglets itself does not have to implement fault tolerant consensus. They do have to implement consensus, I believe. So that's so I'll pause here again for questions.
So the one thing I want to be clear. So if the sequencer dies, does it do a leader election again to get the new sequencer?
No, it initiates a reconfiguration on the virtual log. So it may be like it doesn't have to do a leader election necessarily. It may be that you have like 3 logs effectively. Like, I mean, this is just, I'm imagining this again, I don't know for sure. But let's say we have like 3 loglets on backup. We have a backup loglet, which this is the sequencer, and we have backup loglet 2, where this is the sequencer. And these are just separate instances on the same set of servers. But basically, you could just say that once I detect this one failure, I shall move to the loglet that I am the sequencer of now, and it will reconfigure the loglet itself versus actually doing leader election. So it will send a reconfiguration on it, which tries to reconfigure it to it being the sequencer. So it does not exactly do leader election in the traditional sense of redirection, where you're coordinating to decide who the leader is. It offloads that to the virtual log. That's how I understand it, at least. Please correct me if I'm wrong. Let me just draw those figures again. Yep.
So yeah, if I understand then what you're saying, it instead of doing the election, it just has these fallbacks that are kind of just pre-configured. It's like, oh, the sequencer's dead. What's my fallback? Oh, the fallback is go to runtime number 2 to be my backup sequencer, right?
Right, and that's how I imagine it to be done.
Yeah.
Like, I mean, but that's how this would work effectively. It doesn't actually try to elect these things as a new leader in terms of effectively, when I think of election, like I'm thinking of like, it doesn't discuss among themselves, like to decide, okay, who's the new leader and we shall elect it. It sort of offloads that to the virtual log effectively. So there is no discussion between these servers about who the new leader is. Not in the loglet though. It does go to since all of this is embedded. These effectively talk to each other because they're embedded. But you could imagine the implementation being what they call disaggregated, where the loglet is not on the server itself and it's on a separate set of servers.
Just 2 questions quickly. Do they specify what happens if all the Delos runtime clients die?
If all the Delos runtime clients die?
Yeah, like how many? Is it like, is it 1 per actual application user? There's 1 client?
So yeah, the way they talk about it, let me just find the slide which we were talking about it. So the way they talk about it is that they have a runtime on the client, but you can do something. They have like this implementation of converge versus disaggregated. So basically, because it's a database, if too many of them fail, you will have a total failure. You won't be able to reach a quorum effectively. To do consensus, even if it's not fault tolerant. So what they do is like you don't like if they start detecting, okay, fine, now we have only 3 servers we have only 2 servers and we might not be able to reach consensus. You can sort of reconfigure to a disaggregated loglet where it's on a separate fleet. These are the pros and cons they mentioned of each of the approaches. So converge is what they have on in production, but if they start detecting multiple failures, if they start seeing higher traffic, they basically decouple it by reconfiguring to a disaggregated version, and that is how they achieve, like they say that they achieve higher throughput because a disaggregated log can scale independently from the database itself. Does that answer the question?
Yeah, it does. Yeah.
Cool. Is there anything else?
I think we can keep going.
Sounds good. I think I spoke about what I want to speak about next, which is the loglet. But I'll walk back to the Delos implementation. So the virtual log and the virtual log is implemented with the virtual log is implemented as a client-side library, and so I think the requirement is that the client-side library has to understand how to interact with loglets. So, or there must be some API, some structure that way. But basically, so this part is my addition. I just want to clarify that. I don't think that's in the paper. But basically, it's implemented as a client-side library. The metastore initially went to prod on a Zookeeper instance. Afterwards, they decided to create an embedded metastore. So the metastore itself is on all the metastore itself is the database server. So it's all the same server effectively. And so that's how they've implemented the virtual log and the metastore. These are all the different log implementations. They've got the Zookeeper, they've got the native log, which is what we just talked about. They've got the backup loglet, which is effectively, we can probably talk a bit about that now. So what they say is that like once you seal a loglet, so there's an API called reconfigure modify. A reconfigure modify API is where you can sort of change the sealed loglet. So effectively, you could consider that let's go back here. Yeah. So once we seal this and we are in this use case over here, what the thing is you can sort of the seal loglet you can sort of change the seal loglet. And so suppose if you said, like we are in production for the longest time and now like the Zookeeper loglet is effectively cold, you can basically create a new loglet, which is like you can call it the you can call it the backup cold storage loglet, backup cold loglet, and you can sort of copy all the entries over, which is basically you copy all of these entries over, and then what you do is you reconfigure, modify this entry. So what you do is you can you can sort of like basically say now 0 to 3 0 0 to 3 is the backup cold loglet. And so now you have sort of effectively done a new version. I assume, and this is not explicitly mentioned in the paper, I assume you would have to keep both of these alive until the metastore caches are invalidated. But effectively, you sort of can do a can do a swap of cold parts of the log without actually affecting the production part of the loglets. So that's what the backup loglet they call it. And so this is like every time parts of the log becomes cold, they reconfigure the log to move more and more of it on the backup cold loglet. I also think that you can sort of break this loglet up into multiple loglets where you have like say the backup loglet, but it doesn't span the whole address space of the log. It only spans like the first 100. So you can assume it spans like 100 to 150, and then you rewrite the new version of the log effectively to basically say that this is now 0 to 3 is Zookeeper, 3 to 100 and 3 to 53 is backup, and 53 to infinity is LD loglet. So I think you can do all of those things. I don't know for sure because I didn't run through all these protocols, but this is my instinct, at least, that all of these should be possible. They did talk about the first part in the paper, that you can replace a whole loglet fully. I don't know if you can do a partial loglet like this, but I don't particularly see the protocol stopping us from doing that. Yep. So you do have to seal some part of the loglet, though. So I don't know how that would work. I think that's the only thing that breaks now that I think about it. But basically, for a seal loglet, you can always do for a sealed loglet. You can always do that. I assume the way you would do this is you would probably have to seal this first, create a new LD loglet, and then you can probably do whatever you want with this one. So yeah, so cool. So that's that about the native. And this one, the backup, the log device is again one of the other ones, and then the Stripe loglet. This is one of the other implementations of the loglet they've implemented. I shall walk through that right now. Basically, as you saw in the older loglet, there is in this one there is the sequencer failure, which effectively the sequencer fails, and so here's they have a sort of they built a what they call a Stripe loglet, and so you could sort of you can have it in multiple approaches, which is like a you have. I don't understand the Stripe loglet very well, but I'll do my best. One of them, there are three shards of the loglet, and in each log entry is written to one of these shards. It is possible for you to write a log entry over here like 6, but this is not acknowledged until all the other entries are written. So you would have to basically go, 4, you'd have to go 5, and then 6 would get acknowledged after that. It is again possible that now, considering that you can write these log entries, it is possible that you do things like, you do things you do like when in this state suddenly like this client decides to seal this loglet, and this is a possibility, and it would get sealed at this point. I assume that is why they have like these zombie entries and all of the other stuff, which basically they have to sort of fill these with something, which is effectively a no-op in this case. So that's something they talk about in the paper briefly, which basically they have ways to fill this with no-op. They have ways to repair the loglet where they can fill this to sort of drive some after sealing, they fill this for some reason of repairing failure repairing, but I don't understand that very well again myself. So, yep. So that was the Stripe loglet. Any questions on this? Anything discussion topics?
One of the things I was wondering about, they mentioned, like you said, that it won't fill up. It won't continue until all the numbers have filled. I was wondering what happens if a hole persists and it just gets stuck. What will happen to the tape then, or the virtual log at that point?
Yeah, to be honest, I'm not sure, but like I think like there was something mentioned in the, I think that you're going like there was I did read some of the Corfu paper, which was kind of like which was a related paper to this. One of the things they talk about that if there are holes in the log because the protocol fails or whatever reason, they just fill the log up with they just fill it with no-ops at those points. They also talk about being able to do things like, so you can, they talk about the trimming the cold surface segment. Let me try to find that. They have this, they talk about like being able to skip poison pill entry somewhere. I don't remember exactly where that was, but basically they talk about being able to skip poison pill entry. So I assume there is some way to rewrite, to sort of do stuff with a sealed loglet. And so you can't fill it up with entries because it would break. And so that's kind of like what the Corfu paper said, that they fill it up with they fill these up with no-ops effectively.
Cool. That would make sense in my mind. Yeah.
Cool. That pretty much. I mean, that's more or less. Let's say the Delos implementation, native loglet and Stripe loglet. So yeah, I'm pretty much at the summary now. So like sealing logs, effectively, like in this sort of, I effectively watched one of the other Zoom reading talks before this to kind of understand the sort of failure modes a bit better. So effectively, these are the two cool ideas which David. So, ceiling logs allow us to reconfigure across protocols, which is pretty neat because the implications are pretty amazing. That you can choose, you can sort of choose your different loglet implementations based on your throughput, based on this thing. You're not your design choices kind of expand a little more. You can sort of choose your loglets, and you could choose your different, and you can choose it based on situation too. So if it's a high traffic day, you can change your implementation on that day. You don't have to like sort of plan. You don't have to basically, you're not committed, and so it allows for easier decisions, I guess. And the other one is you can separate reconfiguration into a highly available part and the less available part. And so their idea in that piece was that let me just go back here. So effectively, it is difficult to build all these three components at the same time. You can't build a simple, fast, and fault tolerant. I don't think "can't" is the right word. It's hard to do it. It's simple, fast, and fault tolerant at the same time. So instead of trying to build one, they basically divided and conquered. They can build a simple and fault tolerant metastore plus VirtualLog, and then they build a simple fast but not a fault tolerant loglet. And the combination of the two is simple, fast, and fault tolerant, but each of the individual entities are not any one of the three. So that's that. And these are pretty much the references which I use for preparing for this talk. That's pretty much all I had.
I like how they named the thing Delos.
Oh, right. They have it at the end over here. So this is Delos, and this is Paxos, and this is Corfu. So here, Corfu, Paxos, and Delos. So these are the three these are three databases named after Greek islands, and it was pretty interesting to me too.
Yeah, totally.
A lot of this paper actually reminds me a lot of Kafka. Just because Kafka is an implementation of a shared log, but you can take the Kafka API as sort of the abstraction layer, and then there's like the actual partitions that it maps to. So it in a way feels very similar to Kafka, but it has a stronger API layer between the like metastore like mapping layer and the actual loglets.
Yeah. Yeah, I can see that. Well, this is cool. Thank you for going over Delos with us. That was rad.
That was an excellent presentation too. You did a very good job.
Yeah, you did great, man. Very, very cool.
Yeah, I had fun.
Yeah, and if you want to have fun too, you can sign up. Like, please reach out to Max or myself on Slack or meetup.com, and we will more than happy to set one of these up. We have one coming up in 4 weeks, but we don't have a speaker. We don't have a paper. So if you have a paper idea that you want to talk about and share with everybody and have us learn together, please let us know because we're always looking.
Yeah. If we do not have an external speaker, next month will either be canceled or me or Trevor will present something depending on how we feel.
It's true.
Coming up to it. That's basically what happens.
Yeah. And we don't want to cancel. So yeah.
That's why our cancels are always good.
Is it usually topics in distributed systems or anything goes?
Anything goes. Anything goes. Yeah. We've had talks as far afield as we did Albert Einstein's original paper on relative
the theory of relativity. We've done last month I did a voting algorithm, a secure voting algorithm called Star Vote. We have done programming languages,
quantum computing,
business,
Yeah, business. Yeah, one of my personal favorite topics is organizational theory. So we've done at least 2 talks on organizational theory. Economics
and game theory also tend to work well.
That's interesting. Can you forward me the links to those 2 meetups, the organization theory one?
The organizational theory one we unfortunately didn't record, but I can send you a link to both the papers
That's fine.
that we did. Yeah, find them.
Yeah, we've done. What else have we done? We've done some networking stuff. That's a little less common, but we've done, I think, like 1 or 2. Scott did an excellent overview of the history of graphics.
Graphics in VR, yep.
Yeah, graphics in VR. That was a really cool one. We've done Bitcoin. Someone did the original Bitcoin paper. We've done security. It's been every topic. We tend to get a lot of databases and distributed systems. I think that just has to do with the kind of people in Seattle. I think that's just partially like a function of being in Seattle, and